So yeah, starting with chapter 7, um, which is nuclear physics. Let me just bring the textbook back to the start. I'll be using the textbook and the notes to sort of guide us along, and I'll be using the whiteboard to explain the things. So yeah, atomic, nuclear, and particle physics. So to start it all off, with the discrete energy and the emission spectrums. So I'm just gonna explain the basics with the whiteboard first because I find it a lot easier to go with it that way. So for this, let's take an example of a hydrogen atom. So we know a hydrogen atom has a proton and an electron. So the electrons have multiple energy states. They're kind of shown over here like that. There are many different energy levels. It ranges from n equals 1 to n equals infinity. And these are essentially the various excitation states of the electron. So as the electron gains energy, or as it loses energy, it transitions between these excitation states. So n equals 1 over here is what we consider to be the ground state of any electron in an atom. All the electrons and in all atoms will always prefer to be in the n equals 1 state because that's the lowest energy level. So to give an analogy for that, you can imagine it to be kind of like a ball on top of a hill. At the very peak of the hill, so like if I just draw the hill out, kind of like if we have a valley like that in a hill, and if we have a ball up over here, it's gonna have a potential energy of like mgh, where h is this height over here. Now we know that the ball will prefer to just roll down and just come to the bottom over here, where its potential energy is at the minimum or just at zero. So similarly, electrons are like that as well, is that they always want to be at the lowest energy level. So they always start off at the ground state. So if I redraw the energy levels, so we start with n equals 1, n equals 2, n equals 3, n equals n equals 4, and we keep going up until n equals infinity. So n equals infinity is what you can think of when the atom gets ionized. So the electron has gained so much energy that it just leaves the atom. So how does this relate to the concepts of um, discrete energy and emission spectrums? So we talked about ground state and excited states. So now let's get into the excitations, relaxations, and the discrete energies and the emission spectrums. So, like I said, the electron in the hydrogen atom will prefer to be at the lowest state. Let's say this is the electron. So now, if a random photon, which is carrying energy, comes and hits the electron over here, it'll gain energy. And as a result of which, it'll jump up a energy level and it'll end up at a higher energy state, entering an excited state. So this is called excitation when it absorbs a photon and it jumps up an energy level. It doesn't have to go up by one energy level. It can jump up all the way from here. It can go from one excitation state to another excited state. It really depends on what's the energy of well, how much energy the electron gains. So now, once we have the excited electron, that's all the way up over there. Let me just get rid of the arrows real quick and put the energy levels back. So now we have the excited electron at the n equals 2 state. So eventually it's going to lose the energy and come back down to its ground state. So as it does that, it's going to release energy. Some energy it's going to release. We'll just call that E. And it normally releases it in a form of a photon. which is just a light particle that carries energy. There's not much to it. That's all you need to know for IB at least. Um, and yeah, this process is called relaxation when it emits energy and comes from an excited state to its ground state, or from a higher excited state to a lower excited state. So now this relates to our concept of discrete energy. So this says that energy can only be absorbed and emitted at certain values. So this electron can only absorb a certain energy of photon. So it can only go up to the n equals 2 or the n equals 3 state, but it can't go in between. So those specific energy values can only be absorbed and emitted. And that's discrete energy. So before I continue, are there any questions? How long is the session? Uh, I'd say maybe 40 to 45 minutes. I don't think it'll go longer than that. But yeah, so yeah, I'm gonna assume that it's all good so far and just continue. Also, I'd really appreciate if everyone muted. So now, what is an emission spectrum? So an emission spectrum is essentially all the possible wavelengths that are emitted by an atom. So like we talked about, like the photons gaining energy or losing energy to transition between excited states, we also found out that that energy is discrete, that we can only transition between certain energy states. So we can go from n equals 1 to n equals 2, n equals 2 to n equals 1, n equals 2 to n equals 4, and so on. So for those specific energy values, we can associate them with a specific wavelength. And if we put out all of these wavelengths, we get something known as an emission spectrum. So they will look something like this. These bright lines that you see are the colors that are emitted by, in this case, a hydrogen atom when it's excited. So when it transitions from, let's say, the n equals 2 to n equals 1 state, it releases a photon with the wavelength of 656.3 nanometers, giving us the red color. And each atom has unique emission spectrums. So looking at the emission spectrum, you can actually determine what kind of element you're dealing with over here. As you can see over here, like hydrogens is completely different from helium, which is completely different from mercury, and so on. And yeah, that should be it. Oh yeah, and you also do have the opposite of it, the absorption spectrum. So just like the emission spectrum is what's being emitted when like the atom goes from higher states to lower states, the absorption spectrums are basically when you just shine light at the atom, like of various wavelengths, the the wavelengths at which the photons are being absorbed by the electrons, those sort of disappear from the spectrum. So it gives you this with black spots, like the dark lines. And yeah, that's essentially it for the discrete energy part of the chapter. And now moving on to radioactivity. Before I do that, is there any question? Oh, the absorption diagram? Sure. So, earlier we talked about how when an atom is exposed, like when it absorbs a photon, it goes up a level, and when it releases a photon, it goes down a level. So if you, let's say, have a bunch of hydrogen atoms over here, let's just take a tube in which we have tons of hydrogen atoms, which are all in different excitation states. So just assume these dots are hydrogen atoms. and then we shine a beam of light at it, which contains all the wavelengths in the visible spectrum. So as the light passes through, most of the wavelengths, like most of the light wavelengths, will just pass through normally as if nothing ever happened. But some of the wavelengths will get absorbed by these hydrogen atoms. The specific wavelengths at which it can transition an energy state, those will be absorbed. And when you try to, when you use a spectro, when you do, it's like when you take a, uh, when you use a spectrophotometer to see what wavelengths are present, you're going to get something that looks like this. It'll be like a continuous spectrum over here, like a rainbow, but the energy values at which the atoms transition energy levels, those will disappear, and you get these black lines over there. Does that make sense? Okay, cool. Yeah. Yeah. And I'm just gonna assume that there's nothing else and keep going. How do you identify an atom? Oh, yeah. So yes, it exactly. It depends on the specific frequencies or the wavelengths that are absorbed and emitted. So like you can see over here in this example, is that hydrogen has a peak over here at 656, at 486, at 434, and 410. But meanwhile, helium has a peak at 667, 587, 501, 492, 471, and 447, and 402. Like that, each and every element has a very distinct emission spectrum. And if you use a spectrophotometer, you can actually distinguish every single element in the periodic table because they're all completely different. And interestingly enough, in this semester, I actually got a chance to do that myself, where in one of our labs, they gave us various samples of gases and made us pass light through it. And using the photospectrometer, we had to measure the various wavelengths at which light is being emitted, and using that, we had to determine some of the atoms. So I do know from experience that this works very well. Yeah. And yeah, so let's go on from here. If there are any other questions about this, I'll answer them at the end of the session or as I'm going through. And let's move to the next part, radioactive decay, the thing that seems to scare everyone. Yeah, so before that, let's talk a little bit about the atom itself. So the term nucleon refers to protons and or neutrons. It's essentially just saying the things that you find inside the nucleus of an atom. So that's an easy way to remember it. Then the atomic notation. So when you write out an element or an atom, you give it in this form over here, AZX, where A is the mass number, which is basically the sum of the number of protons and neutrons present in the nucleus. Z is the proton number, which is the number of protons present in the nucleus, and X is the symbol of the element. So for example, if we were to give hydrogen in atomic notation, it would be H1, 1, because it has one proton, this is going to be 1. H is the symbol of hydrogen. The nucleus consists of one proton and 0 neutrons, so its mass number is going to be 1. If you want to give for oxygen, we'd write it as 16, 8, O. O is the symbol of oxygen, 8 is the number of protons, 16 is the mass number because oxygen has 8 protons and 8 neutrons. And like that, you can do it for every single atom, like 235, 92, U. This is uranium 235. And so on and so forth. So normally when you're doing nuclear reactions and atomic reactions, you make use of this form instead of what you do in chemistry, just writing H or CH and so on. Then we have isotopes, which is basically just saying that it's the same element as it has the same number of protons, but it has a different number of neutrons in the nucleus. And as a result of which, it can have different properties in some cases. Next up, we have radioactive decay. So radioactive decay is an unstable nucleus breaking down into a stable nucleus and a radioactive particle. This is a spontaneous and random process. So I don't think the IB needs you to know why certain atoms are unstable and they need to radioactively decay, but I guess it's pretty simple, so I'm just gonna say it anyways. So there are mainly three reasons why we can have radioactive particles. It's when there are too many protons, so too many protons. I'll just write as P. When there are too many neutrons,
Come in. Oh wait, hold on.
Hi. Um, do you guys happen to have any milk by any chance? No?
You're okay.
should have put a do not disturb in front.
No, you're good. Your phone call. Do we have milk left over for tonight?
Does that much
Is it expiring tomorrow?
This is expiring in 3 days, but I don't think I'll drink it.
You don't think you'll drink it?
Yeah.
I can go off for it. Are you fine with me offering it?
Yeah. All right, yeah, sorry about that. Someone came over. I'm in a dorm, so people keep coming in and going out. Anyways, let's just ignore that and continue. So yeah, why do things radioactively decay, or why are atoms unstable? It's because there are too many protons, they have too many neutrons, or they might be hit by some form of radiation, some other form of radiation, or receive some form of energy that makes them excited, and as a result of which they need to decay. And yeah, essentially they decay in order to, so like in the cases of where they have too many protons or too many neutrons, they decay so that they end up with a more stable ratio of protons and neutrons. And in the cases where they're excited, they just emit the energy that they have been excited by. But you don't need to know this for IB. Just like if you want to make sense of why they decay, you could use that. And yeah, so for the IB, there are only three types of decay you need to know: alpha decay, beta decay, and gamma decay. Oh, oops. Yep, gamma decay. And there are actually about 8 different types of radioactive decay, but you don't need to bother with any of them, any of the other ones, just these three. And yes, also, radioactive decay is spontaneous and random, which means they can happen at any point of time, anywhere, like completely random, and it's impossible to predict exactly when a single atom will radioactively decay. So when we want to observe radioactive decay and like to see what exactly is happening, we generally use a large sample where we have like something like 10 to the 25 atoms, 10 to the 25 radioactive atoms to really see what's happening over here, because it's impossible to say when exactly one atom is going to decay. And now let's look into each of these decays. So alpha decay is when you have a large unstable nucleus breaking down into a more stable nucleus and emitting something called an alpha particle, which is just a helium nucleus. So I believe the textbook has an example of alpha decay, so I'll just be using that to help out over here. So yeah, so that's an example of alpha decay. So we have uranium-238 over here, which decays into thorium-234 and emits this alpha particle. So note alpha particle is the nucleus of a helium atom. So it's not correct to write helium. You must write 4 2 alpha. Alpha particles always have a charge of +2, and as a result of which you can actually detect them using an electric field. So if you have an alpha particle, so like let's say you have an electric field over here, which is going something like that, right? Or actually, no, let's make it a little simpler. Let's just say that you've got a positive charge over here and a negative charge over here, stationary, okay? And if you have your alpha particle that's just going through over here, as it goes over here, it'll bend this way and go sort of like that. This is because the alpha particle has a +2 charge on it, and it's going to be attracted to the negative charge over here, and as a result of which it's going to curve. And that's how actually scientists like managed to see what exactly alpha particle were and determine what charge it had by putting it through an electric field between two opposite charges. So alpha particles have the mass of a helium nucleus, which is 6.64 times 10 to the power minus 27 kilograms. I don't think you need to know it. It might be in the data booklet, I'm not sure. But in most cases in the exam, they'll give it to you if you need to work with it. And its penetration power, as in how long it can go before completely disappearing or ionizing or something like that, is just a couple of centimeters of air. So once you have an alpha decay in, let's say, the air like right in front of me right now, after a few centimeters, that alpha particle is just going to disappear. It's either going to absorb some electrons and become a helium, or it's going to bond with some atom and form a compound. It really depends on the surroundings, and you can't really predict what happens over there. But in general, after a few centimeters of air, you won't see any alpha particles. Next up, we have beta decay. So for beta decay, we now have, oh yeah, here are more examples of alpha decay. So you have radon 224 decaying into, uh, what was Rn again? Yeah, 220 Rn. I'm just going to call it Rn for now. I don't remember what Rn stood for. And alpha, and an alpha particle. So you can make sure that the masses are balanced by seeing that the mass numbers and the proton numbers on both sides are equal. That's how you know for sure that you've done the right type of decay. Next up, we have beta minus decay. So in beta minus decay, you have a neutron in a nucleus breaking down into a proton and emitting an electron and an antineutrino. So here's an example of a beta decay. You have thorium 234, which breaks down into 234 prota. I don't know how to say this. Prota protactinium, I think. I'm just gonna call it that. Protactinium and a beta minus and a neutrino and an antineutrino. Well, an antineutrino, we're gonna get to that when we get to 7.3, which is the subatomic particles. And for the most part, you just ignore the antineutrino because all it does is carry some energy, but it's completely massless, so it's often easier just to ignore it because it doesn't have much of an effect. And yeah, so the beta minus particle is just an electron. And once again, you can take the sum to make sure that the masses balance out in both cases. So now the electron has a charge of E minus, while the beta particle has a charge of E minus because it's an electron. It has the mass of an electron, which is a constant given to you in the data booklet, though I don't think you'll ever have to use it. And its penetrating power is a few millimeters of paper. So if you have beta decay happening, and if you put a piece of paper in front, it probably won't go through the piece of paper. For the same reasons why the alpha particle couldn't go past a few centimeters of air. And once again, you can detect detect it using a electric field. So if you have a beta particle, a beta minus particle going through the electric field, as it approaches, it's going to curve towards the positive charge because opposite attracts. And I believe there's also beta plus. So in this case, like in beta minus, you had a neutron breaking into a proton and an electron. In this case, you essentially have a proton absorbing a like emitting a positron and becoming a neutron. So positron's just like an electron except with the positive charge. That's all you need to know. You won't have to deal much with beta plus decay. You just need to know what it is. You might have to just write an equation in this form. So earlier we had electron anti-neutrino being produced when we had beta minus decay. But for beta plus decay, you're going to have a neutrino. I should have cleared that out earlier. So it's an anti-neutrino for beta minus and a neutrino for beta plus. And yeah, you'll probably just have to write out an equation like this that they might say like, oh, sodium 22 decays into neon 22. Write the beta positive decay for it, and you can just write this thing out. Just make sure that the masses are balanced and it should be okay. Next up, we have gamma decay. So, like I said earlier, we had three kinds of the three reasons why we have um, radioactive decay is when we have too many protons, too many neutrons, or when it's just excited. So in case of too many protons or neutrons, you're going to either have the alpha, beta plus, or beta minus decay. But when an atom is excited, it does the gamma decay. So what exactly is gamma decay? It just goes from an excited state to a non-excited state and releases a gamma particle. And that's literally just it. The gamma particle is just a photon. It has no charge, it has no mass, but it is the most penetrating out of any of the radioactive decay. It can go through a few centimeters of lead, no problem. And this is the one this is the scariest one out of them because it's really hard to contain this kind of decay. Before I move on, are there any questions? Let me just it's palladium. Yeah, you're right. It is palladium. So yeah, thank you for that. Wait, no, is it? Okay, no, I need to check it now. So, radon. Wait, what's Ra then? Radium. That's right. So that's radium to radon. And yeah, are there any questions about this? Yeah. Can you quickly explain an example equation for one of the decays? Okay. Yeah, I can do. So I'm just gonna reuse one of the examples from the textbook to make it easier. So I'm just gonna take the uranium-238 one because that just goes down to thorium, so it's easier to deal with. Oh wait, can you all see my screen? Just to make sure. Yeah, okay. I think it might be an error at your end. Don't worry, this thing is being recorded, so it'll be up not too long after the session finishes, and you can access it from there. I'm really sorry if it's not working out. And yeah, so let's continue with the examples. So we have uranium-238, and we're being told that it undergoes alpha decay. So we know that alpha is gonna have 4, 2, right? because that's our helium nucleus. It has two protons, two neutrons. So it has a mass of 4 and a proton number of 2. So now to determine what our mystery element over here is going to be, let's just say we're told it's thorium. In most cases, they just tell it to you. And now our both sides must be balanced. So over here we have 92 protons and we have 2 protons over here. This side must also have a total of 92 protons. So this must have 90 for the conservation of mass. This has our uranium has 238. Our alpha has 4 mass number. So our thorium must have 234 mass number in order to balance the equation. And that's usually what you have to do for the radioactive decay equations. You just have to write these equations out. When we go to 7.2, you'll actually learn how to calculate the energy for these decays, but that's for later. Why a series of alpha decay and 2 beta minus decay or beta plus forms an isotope. Okay, yeah. Yeah, I believe it is 2 beta minus. So let's just continue with this, okay? So we have thorium 234, right? And let's just say this undergoes beta minus decay. So for beta minus decay, we know that it's going to release an electron. Sorry, let me do an electron instead. -1, 0, and an antineutrino. 0, 0. So we have proton number 90 over here and proton number -1. Now our mystery element over here, whatever it is, must have a proton number of 91 in order to balance it out. But its mass number is just going to remain the same as 234. Now just to make sure, I'm just going to check what element this is. So proton number, oh right, it's just protactinium, Pa. Yeah, that's going to be protactinium. So we have Pa234 over here. That's after undergoing 1 beta minus decay. Now if we undergo another beta minus decay, so 234, 91, Pa. Since it's a beta minus decay, it's going to have an electron and an electron antineutrino. And now looking at this, it's 91 on this side and it's -1 on this side. So our mystery element must have 92. Oh, and look over here, 92 is just uranium. And the mass number is going to be 234. So now look over here. After doing an alpha decay and 2 beta minus decays, we get uranium 234, even though we started out with uranium 238. Same number of protons, but different number of neutrons. Hence, they are isotopes. Does that clarify it? Okay. Yeah. Cool. And with that, let's just move on to the last part of 7.1, which is just the decay. So half-life is the time taken for half of the nuclei to decay. So like I said earlier, when we observe radioactive decay, we take massive samples of like 10 to the 25 atoms and so on. So half-life is basically the time it takes for half of our sample to decay. And this, as long as you take a large enough sample, this value is always going to be the same. So I don't think the SL part needs you to do the radioactive decay calculations, as in the n equals to n e to the minus lambda t. I believe that comes in chapter 12. Yeah, over here. So I am not going to do that, but I can do that if you guys want me to go over it. So just like say a yes or no real quick. Yep. Okay, then. So now let's talk a little about modeling radioactive decay. So here's an equation that really helps to see how many atoms you have remaining of an unstable atom that's undergoing radioactive decay. So if you have a massive sample over here, let's just say there's a sample with like 10 to the 25 atoms in it. And you know that it has a half-life. I'll just say T half of, let's just keep it simple, 2 seconds. So in 2 seconds, it's going to be halved. So let's just draw out a graph for this. This is going to be the number of atoms, and this is the time passed. So we start over here with 10 to the 25 atoms. That's what we initially have. At time equals 0, that's how much we have. Now at 2 seconds, we know that it's going to be halved. So let's take about half over here. That's going to be about 5 times 10 to the 24 atoms. It's been halved now. And let's plot that point over here. Let's take 2 seconds later, at 4 seconds now. This is 2.5 times 10 to the 24. So you get a point over here. And as you keep doing it, you're going to get a plot that looks something like this. It's going to come out, okay, it doesn't look that nice, but it's like a curve, a downward curve, an exponential curve. So how do we model this equation so that we can find out, like, at any given point of time how many atoms are remaining in our sample? So for that we have the equation n of t is equal to n naught e to the minus lambda t. So I'm not going to go into how this equation is derived because that requires differential equations, and most of you don't need to know that. So just assume that this is true for now. And so NO is the initial amount of atoms we have. So I'll just write initial over here. Lambda is something that we call the decay constant. Now I'll tell you what the decay constant is. And T is the time passed. So the initial value is just 10 to the 25 in this case. What is our lambda? So lambda can be given by a simple formula. It is the natural log of 2 divided by the half-life. And that's just your lambda. So if you want to know why this is your lambda, this actually goes into the derivation of Euler's number, I think. So just go with this for now. And yeah, that's how you plot out radioactive decay. This is a model that helps you see at any given point of time how many atoms of the radioactive sample is going to be left. And yeah, that's just that's the equation. And of course, you also have the activity, which is essentially just the derivative of it. Or so right, yeah, activity. Activity is the rate at which decay occurs. Its units is becquerel, which is also just decays per second. So the activity, in a similar fashion to radioactive decay, is given as A of t is equal to the initial activity e to the minus lambda t, where your initial activity is equal to lambda times the initial number of atoms. And that's the equation that's given right over here. And yeah, that's all there is to 7.1. Before I move on to 7.2 and 7.3, are there any questions? I'm gonna assume that it's all good so far and just move on to the next part, and my favorite part of the IB syllabus actually. which is nuclear reactions. This is what I do for a living, now at least. Oh, yeah, sorry, I should go over this real quick as well. So, the fundamental forces and their properties. So, we know what forces are, but in nature, there are actually four main types of forces that exist. And they're kind of categorized depending on the range at which they act or where they act and between what they act. So we know what electromagnetic interaction is. It's between charged particles. It's given by Coulomb's law and it has infinite range. So it can act like even if you're at two distant ends of the universe, you're still going to feel the electromagnetic force. Next, you have weak nuclear interactions. So this acts on protons, neutrons, and electrons and neutrinos in order to bring about beta decay. You can think of weak nuclear interactions to be the interactions that hold the subatomic particles together. So, like what holds a neutron together or a proton together, or what is the force that's keeping the electron inside the neutron when it breaks down into a proton, things like that. Then you have the strong nuclear interaction, which is this is a mainly attractive force, and this is the force that holds the protons and neutrons together inside of an atom. And finally, you have gravitational interaction. This is the force between two masses. And this also has infinite range. So weak interactions and strong interactions have very short ranges, which I believe you should keep in mind is at 10 to the minus 18 and 10 to the minus 15. It could be an MCQ question in paper one. And yeah. So yeah, that's actually it for 7.1 now. And before I move on to nuclear reactions, let me just see. Okay, no questions. So we're good to move on to nuclear reactions. So yeah, let's go through this a little quicker. I thought I'd be done with the session by now, but yeah, anyways, that's irrelevant. So nuclear reactions. So let's start off with the concept of mass defect. So when scientists actually managed to measure the masses of protons and neutrons, they noticed and atoms, they noticed something was really odd. The masses of atoms did not match up with the sum of the masses of their nuclides, of the nucleons and the electrons. Then they came to realize that there's something called mass defect. So essentially, when you have a bunch of, like, let's say protons and neutrons, let's just say that these are ton of like four protons and neutrons. When they come together to form a helium nucleus, they actually release some energy. And as a result of this energy released, its mass is actually less than what it initially was. And this relates the to Einstein's equation, the famous equation that we all keep hearing about, E equals mc squared. It essentially says that mass is just another form of energy. You can make mass into energy, as in the case of the protons and neutrons forming helium. So now this difference in mass is what they call mass defect. It is the difference in the mass of the nucleus and the sum of its nucleons. So in the case of helium, your mass defect is going to be the mass of helium. This is the symbol sort of a mass of helium minus the mass of two protons minus the mass of two neutrons. Actually, you write it the other way around normally because the helium mass is smaller. Actually, I should do that. So we have two protons plus two neutrons minus the mass of helium. The mass of helium. And this is equal to your mass defect, which is given by the sign delta. That's actually small delta. And yeah, So you can make use of that to find out what is known as the binding energy. So binding energy is the energy released when a nucleus is formed, or the energy required to break apart a nucleus. Binding energy is simply the mass defect times c squared. We're just applying E equals mc squared over here. So we know the mass defect is the mass that gets converted to energy, so multiplying it by c squared gives us the energy that's released when forming a nucleus, or the energy that's emitted, sorry, the energy that's required in order to break apart a nucleus. And now we can make use of mass defects, like the similar concept, when we want to find out the energy in nuclear reactions. So now, oftentimes in chemistry and also in this chapter, you'd see like reactions happening between atoms. Let's pull up an example from here. So, oh, have they not given any? Oh yeah, they have. So like this, like the alpha decay, for example. You're having a decay over here, and you're being told that it's release energy, but where does this energy exactly come from? Like, why does decaying, or why does various uh, nuclear reactions produce energy? Well, that comes from the fact that each atom and each and every element in the world has a different binding energy. And the differences in these binding energy is what actually releases the energy in reactions. So you can sort of imagine it in this way. So let's take the example of radium decaying into radon. So you have a radium nucleus. Let's just say that's a radium nucleus. It has 88 protons. So let's just say 88 protons. And it has I believe, okay, give me a second. I'm not that good at mental math. It has 138 neutrons. So this decays into radon, which has 86 protons and 130. Wait, hold on. It has 136 neutrons. And it gives you an alpha particle, which has 2 protons and 2 neutrons. So you can imagine the reaction actually happening something like this. So initially, our radium breaks down into 88 protons and 138 neutrons. And because of that, it consumes whatever is the binding energy of radium. Let's just call it binding energy Ra. And then these protons and neutrons reform into the alpha particle and the radon. And then it releases the energy of the binding energy of radon and the binding energy of the alpha particle. Does that make sense to you guys, or is it confusing? Do let me know. I can slow down and re-explain this. One more time. Okay, yeah, no worries. So, like I explained a little earlier, we know that binding energy is the energy that is required in order to break apart a nucleus, or in order to form, or the energy that's released when a nucleus is formed, right? So when we have this reaction that's taking place where you're going from radium, Ra, to radon, Rn, what's essentially happening is this radium is completely breaking down into protons and neutrons. The radium initially had 88 protons and 138 neutrons, and now it's going to radon, which has 86 protons, 136 neutrons, and it's going to an alpha particle, which has 2 protons and 2 neutrons. So when it breaks down, it takes in the energy of the binding energy of radium. which is going to be, I'm going to give it an arbitrary number for now, just for the sake of an example. These are not exact values. Or actually, I could probably pull up the exact values. Just a second. So yeah, that's the binding energy of radon. It's about 7.66. So it takes 7.66 MeV of energy and then it breaks down into this. And then these reform into radium and alpha. And as it reforms, it releases whatever binding energy of radium and radon and helium and alpha particle is. So let's just quickly find those values. This is 7.69. And for alpha, well, alpha is actually really close to helium. So I'm going to use the value for helium over here, which is just 7.07. And yeah, as you can see, the energy being released when you reform these atoms is significantly greater than the energy that you had to break down this radon. And because of this difference, you actually have energy being released in nuclear reactions. And you can find this out for pretty much any reaction. You'll see that the binding energy for the products will always be greater than the binding energy of the reactants, because of which it releases energy. So does that make sense? Okay, cool. Just hold on for a second. No, the mass on the left will actually be smaller. The energy released will be greater because remember, binding energy is based on the mass defect. And mass defect means if you have a greater binding energy, there's a greater mass defect. Hence, the mass of the particle will be smaller. Does that make sense? Okay, cool. And this is actually like going deep into seeing where the energy comes from in nuclear reactions. And well, this is actually the binding energy per nucleon, but if you account for the per nucleon fact and do it, it still comes out to be greater. So what kind of questions will you be asked about this in the IB? Because that's what is important over here. So if you want to find out the energy released in any kind of nuclear reaction or decay, you basically calculate the mass difference as they have done over here. The mass of the reactant minus the mass of the products. That gives you the mass defect or the mass difference, and then you can just multiply that by c squared or use the conversion factor over here, 931.5 MeV, in order to give you the energy for the reaction. And yeah, that's essentially the type of calculations that you'll be asked over here. Oh yeah, and in some cases you will have reactions that give you negative mass. The mass difference is going to be negative. This essentially means that you need to provide energy for the reaction to happen. But I don't think you'll ever be asked about an instance where you have to talk about negative energy or ones that you have to give energy inside. And let's go and look into the two types of nuclear reactions that we have right now. So the two types of nuclear reactions we have are nuclear fission and nuclear fusion. So fission is when you have a large atom, unstable atom, that breaks down into a smaller atom or multiple smaller atoms, which are more stable. That's fission. And nuclear fusion is when you have two smaller atoms or nuclei that combine to form a larger nucleus. So you have two smaller ones that basically combine with each other in order to form one larger nucleus. So both fusion and fission in general release energy, but what exactly determines whether fusion or fission actually releases energy? Well, in each instance, you'll probably have to do the mass difference equation that we've been using over here, the delta M, and calculate the mass difference, see the energy. If it's positive, then it'll do fission. If not, it'll do fusion. But there's an easier way to actually look at it. So there's something called a binding energy curve. It is this, where is it? Yeah, it is this fancy curve that you see over here. This here is known as the binding energy curve. What exactly is this? So this is just plotting the binding energy per nucleon. So you take the binding energy divided by the mass number, and it's plotted on a graph over here. Essentially, all the atoms smaller than here will do fusion and produce energy by it. And all the atoms greater than this peak over here will do fission and produce energy. Because it's at that point where your fission produces energy, or fusion produces energy. You can calculate it and figure it out. I'm not going to do it because you don't really need to look too deeply into it. And this peak is always at nickel 62, which is considered to be the most energetically stable. You do have an odd peak over here, and that's that's probably helium 2, I think. Helium 4. Yeah. But this odd peak just says that this helium is significantly more stable than the other atoms. And with that, that's the end of 7.2. Are there any questions here? Bigger the atom, the more the mass defect? Not necessarily. The mass defect completely depends on the stability of the atom. You'll sometimes, like in general, the more stable the atom, the greater the mass defect. And you don't need to, I mean, you can think of it in this way. So the larger the mass defect, the more stable it is, so it's more favored. So the one that is more stable, okay, no, I'm actually going in a circle over here. How do I explain this? Let's see, just give me a second. Actually, I don't have an exact way to answer it. Yeah, the greater the mass defect, the more energy released, and the larger the mass defect, the more stable an atom. Just keep that in mind for now. I'm finding it difficult to explain why exactly that's the case without going into something that's completely out of the realm of IB. So just go with that for now. I don't think you'll be asked about why um, greater mass defect means more stable. Yeah, more energy release is more stable. That's exactly it. Yeah, I mean that is if you decide to do nuclear physics in uni, which is fun, by the way. Uh, fission is when the Be over N and Be both be greater for the products. Yes. So when your product's binding energy per nucleon and total binding energy is greater, then fission is favored. If it's the other way around, fusion is favored. I feel like it's better if you make use of. Yes, energy isn't always released in both. It depends on what the component, what the reactants are. So if you take two deuterium atoms or hydrogen 2 and you perform fusion on them, you will produce energy. But if I take two uranium-235 atoms and try to perform fusion on them, you can like try doing the calculations yourself. You'll see that it will not produce energy. So a particle can either undergo fusion or undergo fission and produce energy, but not both. Okay. Uh, I'm going to move on to the weird part of this chapter. So this part of the chapter actually looks into the it's mainly focused on the three elementary particles: quarks, leptons, and exchange particles. I'm going to go over quarks and leptons, but not exchange particles because I am not entirely sure about them. I found on SOCOS a little confusing, and it is confusing in general, so I'm really sorry about not covering it. I can try and fit it in at the start of my next session if you guys would like, but for today I'm not gonna go over it. And yeah, with that, let's just start with the structure of matter. So, elementary particle, what exactly are they? So, elementary particles just refer to the particles that have no smaller components. So, go, you can't break them up into anything smaller. So, like for example, if you start with me as a person, you can break me down into the various carbon and hydrogen and oxygen atoms that make me up. You can further break down those atoms into protons, neutrons, and electrons. And according to this theory, the three main elementary particles are quark, leptons, and exchange particles. So if you look into those protons, neutrons, and electrons, you'll find the quarks and the leptons and the exchange particles. And you do also have something called antiparticles. So antiparticles are essentially, they all have the same mass but opposite properties. So what exactly are these properties and all? Let's look at them together now. So let's talk about quarks first. So quarks are like these really tiny things that pretty much make up everything, like all the protons and neutrons. So the main thing you need to know about quarks is that there are six main types of quarks. There's up, down, strange, charm, bottom, top. Each one of them have charges. So the up, charm, and top quarks have a charge of plus 2 by 3e. Meanwhile, down, strange, and bottom have minus e by 3 charge. All quarks have something called a baryon number. I'll get to why baryon numbers are important, and strangeness. So strangeness is a unique property just to the strange quark, which is exactly why it's called the strange quark, because it has this other one. So now what exactly are antiparticles? Now looking at this. So an antiparticle is the same as this. So like if I take an anti-up, for example, it'll be just like an up particle, but with the exact opposite properties. So it has a charge of plus 2e minus, and anti-up will have a charge of minus 2e minus. Sorry, minus 2e. It has a baryon number of 1 by 3. The anti the anti-up will have a baryon number of minus 1 by 3. Now, using that same example for strangeness, because that's a unique one, it's all I should talk about it. So, strange has a charge of e by 3, minus e by 3, but an anti-strange will have a charge of e by 3. Strange has a baryon number of 1 by 3, but anti-strange will have minus 1 by 3. Strangeness is minus 1, so its anti-strange will have a strangeness of plus 1. So why exactly are these baryon and strangeness? Why exactly and charge is important? So just like we had in like chemical reactions and atomic reactions, we knew that charges and masses must always be conserved. Just like that, when you have interactions with quarks and subatomic particles, charge, baryon number, and strangeness must be conserved in every single instance. So you can think of baryon number to be the quark equivalent of mass. And strangeness is just a unique property. And in most cases, they just simply balance out, so you don't need to worry about it too much. But yeah, and when I say quarks make up stuff, you can actually see how exactly they make up stuff. So for example, we're being told that a proton is two up quarks and a down quark. Let's see what that means. If you have two up quarks, it's going to have a charge of 2 by e 2e by 3, 2 times 2e by 3 plus minus e by 3. So now if we sum up all these charges, so that's from the first up quark, that's from the second up quark, and that's from the down quark. Was it a down quark? Yeah, it was a down quark. Minus e by 3. If you sum this up, you will get the charge of plus e, which is exactly the proton charge. And like that, you can try out for the neutron example that they've given over here. We have an up quark and two down quarks. So an up quark has a charge of 2e by 3. The down quark is minus e by 3 each. And the charge is 0, which is exactly our neutron. So yeah, that's exactly how the charges are. Now, just some other additional terms related to quarks. So there's something called a hadron. This is basically any particle that's made of quarks. Almost everything we know is a hadron, technically. Well, protons and neutrons are hadrons, but electrons are not hadrons. More on that later. Now, a baron is a special type of particle that's made of exactly three quarks, no more, no less. And a meson is a particle that's formed when a quark and an antiquark must combine. So all quarks have baryon numbers. The baryon numbers in all reactions must be conserved, just like mass. Now, the table I just showed you about the properties, you don't need to remember them. It's all in the data booklet over here, as you can see. So it's telling you what quarks have the charges 2 by 3e, and all of them have the baryon number 1 by 3, and which has minus e by 3. And that's the note about the strangeness. So just remember, whenever you have like things that involve quarks, where you have quarks having interaction, like for example this interaction over here, just remember all you need to do is make sure that the baryon number, the charge, and the strangeness is balanced on both sides. And that's all. That's all there is to this. Similarly, we have the leptons. Leptons, just like quarks, there are 6 types of them, though leptons work a little differently. So for leptons, you have your basic leptons, which are electrons, muon, and tau. And each of them have their own neutrino, which is given by the sign of V and the subscript of whatever particle they represented. So the neutrinos have no charge, but each of the lepton has a charge of minus E. And just like quarks have the baryon number, leptons have something called the family lepton number, which is given by L and the subscript of whatever family it belongs to, whether it's the electron, muon, tau. So each lepton and its neutrino have whatever like has a +1 for its family and 0 for the other ones. And just like baryon numbers, lepton numbers must be conserved as well when you talk about things involving leptons. So essentially, all you're doing is your atomic reactions and your chemical reactions again, except you're dealing with these new particles over here. And you just need these numbers to be balanced. For the most part, as far as I can recall, all you'll have to do is like complete reactions by like adding in an electron or adding in a up quark or something like that. Or you'll have to balance them just like you do in chemistry. And in paper one, you could be asked to look at various interactions and say whether they are possible or not. You know whether they're possible or not by making sure that the baryon, the lepton number, the charges, and the strangeness are balanced on both sides. And with that, that should be about it for most of chapter 3. I can go a bit over exchange particles, but I'll stop myself at Feynman diagrams. Before that, are there any questions? Hmm, well, there is Chris Dorner. You could check him out. What's a pion? A pion is just a type of lepton. Oh, wait, no, never mind. No. Hold on. A pion, I believe, is uh, it's I think it's a hadron. I'm not sure. I need to check. Yeah. So pions are an example of mesons. So, oh right, I skipped over mesons. Oh, I'm so sorry. Right, a meson is a particle that's formed when a quark and an antiquark combine. So when a quark and its respective antiparticle combine, they form something called a meson. So a pion is a specific example of a meson. When you have a up quark and an anti d and an anti down quark, when they interact with each other, it forms a pion. That's literally it. Neutrinos. So right. What exactly are neutrinos? So neutrinos are essentially, so we have our three types of leptons, right? The electrons, the muons, and the taus. The neutrinos are essentially just chargeless and massless equivalents of its respective leptons. You can just think of it to be that way. Because they have a lepton family number, but they have no charge. That's all they have. That's all there that you need to know about neutrinos. You just need to know that they're massless. The lepton number depends on whatever family it belongs to. And yeah, that's literally about it. So if an up quark and an anti-up join, they form some form of meson. Yeah, so pion is just a specific meson between a up quark and an anti-down quark. Well, in general, if a particle and its respective antiparticle interact with each other, they just destroy each other. So if you have a up quark and an anti-up quark, and you bring them together, they just vanish. Both of them just go poof. And yeah, I can put in I, I think, okay, let's see. I think there's a question. After that, I'll put in a quick note for, oh, in real world, how these quarks even joined. Uh, yeah, that's where exchange particles actually come into play. That looks a little more into detail into how exactly they interact. But in most cases, we can't really control how quarks interact with each other. They just happen and we just observe it. How they're being observed, you don't need to know that. It is quite complicated. Even I fully don't understand it. But yeah, I can take a quick look at exchange particles for you to show what these interactions are like in a way. And yeah, so let's move on to exchange particles. So we know that these interactions between quarks and stuff keep happening. But what exactly happens between them that causes energy changes and stuff like that? So taking an example of two electrons about to hit each other. So let's say we have an electron over here. Actually, no, let's not use a circle to show it. Let's make it E minus. That's going like this, and E minus that's going like this, right? So we know by Coulomb's law that these two will never touch each other because they repel each other, and they should like basically just go off in opposite directions. But what exactly happens over here? That's where exchange particles come into play. So when these electrons actually, well, hit in quotation marks each other, they don't really touch each other. What essentially happens instead is you have the electron going, let's say that's one electron, that's another electron. When they come close to each other, one of them releases some energy, which the other one absorbs, and as a result of which they just divert their paths. That's essentially what happens if you look very, very closely. Because we know by Coulomb's law that things can never touch each other because they'll always repel each other. And that's where the exchange particles come in. There are certain types of exchange particles you need to know about depending on what kind of interaction it is. I believe they're all given in the data booklet, yeah. So for gravitational interactions, you're gonna have a graviton as your exchange particle. For weak interactions, you're gonna have the bosons. W means boson, that's the symbol for boson. For electromagnetic, you're gonna have photons or gamma particles. For strong interactions, you're gonna have gluons. And that's essentially what happens when your quarks and stuff react. They release these exchange particles or absorb these exchange particles, which causes the changes to happen. And there are some videos, there's a video I can link that really explains how you can make use of the Feynman diagram to really understand how, like, what exactly is happening in this instance. I'm going to link it right after the end of the session. You can take a look at that. But for now, I'm actually going to bring the session to an end over here. And before that, are there any questions? This is topic 7, nuclear physics. Uh, yeah, about that. I'm not really sure. Just take a look at the video and watch it. That might help you. I'll link it right away. But yeah, I'm not really sure how energy is conserved. We haven't gotten to that yet where I am. Are there any other questions? Yeah, no worries. Uh, yep, I'm gonna end the recording now.